Okay, so we've got quite an exciting video today. If you like physics, that is. We have a few little formulas to derive for the oscillations of a spring. So let's first imagine our spring looking something like this with a weight attached to the end of it, and it oscillates backwards and forwards like this, and let's call this its rest point. And this length here is going to be the maximum extension, okay? Essentially the maximum displacement or distance from the rest point. Let's call this L. Essentially the spring moves backwards and forwards, and we're trying to find an expression that, given a few facts about this spring, we can determine the force on the spring at any given time and the spring's position at any given time. So the first thing to note about this spring is we're going to be assuming that the spring itself is massless, and that the spring itself is the only mass that we need to consider. Every spring has a spring constant, and this determines essentially how much energy you need to put in to move the spring, if I understand that correctly. It's a bit more complicated than that, but as we'll see, at any given point, the elastic potential energy of this spring, let's call this E, energy elastic, is equal to 1/2 times the spring constant times the extension L squared. Simple enough. And obviously the kinetic energy of any object really is just equal to, very simply at least, 1/2 mv squared, where v is velocity, but we can call v L dot, why not? 1/2 m L dot. I don't like that, that looks like an I. Let's call this, instead of L, let's call it X, why not? Again, it's just a dummy variable, it doesn't really matter what I call it. Kx squared, 1/2 whoops. Oh, I've really bugged this up, haven't I? 1 second, folks, let me just fix my variables. Alright, this can be also written as 1/2 x dot squared, where x dot is the time derivative of the position x, okay? So the rate of change of x is the velocity. So let's, using these facts about this spring that in my country it is taught, you know, when I was 13, very simple facts. Let's take these simple facts, these very simple truths about the spring, and apply them using Lagrangian mechanics to get an expression for essentially the acceleration of the spring. We get that Lagrangian is equal to the total kinetic energy minus the total potential energy, which we've already laid out is just 1/2 mx dot squared minus 1/2 k x squared. Okay, so using the Euler-Lagrange equation, we get the derivative with respect to time of the partial of the Lagrangian with respect to, in this case, x dot is just equal to the partial of the Lagrangian with respect to x. Okay? First of all, let's take the partial of the Lagrangian with respect to x. essentially we treat any variables other than x, yes, including x dot, as if they were just a constant. So this, in this case, would disappear, and we'd just be differentiating this function with respect to x. Okay, and using the power rule, it's pretty easy to see that this is just minus kx. Next, let's go ahead and find the partial of L with respect to x dot. This is just simply the same process. We're just applying the power rule to this variable. 2 comes down, this is just mx dot. And now taking the time derivative of this, d over dt of mx dot is simply mx double dot. The mass times the acceleration of the spring in this case. So, we can write this using the Euler Lagrange equation. We can form an equivalence between these two. Mx double dot is equal to negative kx. And this is essentially a second order differential equation that you can find. You can solve this in order to find an explicit expression for the position at any given point in time. Now let's make the assumption that the initial time is when we apply this x, we apply this displacement to the spring and then let it go, so it begins oscillating. Let's not call the time 0 at the rest mass while it's already got a velocity. Let's say that t0 is when it's got 0 velocity. We're just holding the spring here and letting it go at a distance away from the rest point. Okay, so very simply what this means is x of 0 is the initial x, which is very simply just equal to, well, whatever this x is. Let's call this d. It doesn't really matter, let's just call it d for distance from the rest mass. And our assumptions ought to indicate that x prime of 0 is just x dot naught, which is just also, oh, we're saying that this is 0, right, because this is just 0. Its initial velocity is just 0. Okay, so we've got our initial condition set up. And what I'm going to do is actually use the Laplace transform to solve this. To do that, I'm going to write these both on the same side. I'm going to get mx double dot plus kx is equal to 0. And what we're going to do is we're going to take the Laplace transform of both sides. Okay? The Laplace transform of 0 is just 0. And the left hand side is a bit harder. Mx double dot, and because of the linearity of the Laplace transform, we can write this as 2 Laplace transforms kx. The easiest to deal with is just this Laplace transform of kx. This is just k times the Laplace transform of x, which we can't simplify right now, but let's just denote the Laplace transform of x as just big X over S. Okay? So we get here, this is just K times big X of S. And this term here is a bit harder too. We can take the M out, but that's about it. But if we've got a differential equation, let's say y prime prime is the variable, well, the Laplace transform of this is just S squared times y, big Y of S, minus S times the initial y minus the initial y dot, or the initial y prime, whatever it may be. So in this case, we're just going to get, for this term, m times the Laplace transform of big X of s, which is just s squared times big X of s, minus s times the initial x, which, as we stated here, was just d, minus sd, and x dot 0, sorry, the initial velocity is also just 0. So I'm not even going to bother writing that. Plus k times big X of s is 0. We can distribute, we get ms squared times big X of s minus msd plus k x of s is 0. I wouldn't recommend watching this video, by the way, if you haven't done the Laplace transform yet, because this will look like absolute alien speak, but let's push on. We can factor out the xs from these two terms and move this to the other side. We get that the Laplace transform of x with respect to s is just msd over m s squared plus k. Okay? Now, let's factor out an m from this bottom denominator here. We get msd over m s squared plus k over m, which is just sd over s squared plus k over m. Okay, and we can write k over m, and I'll show you why I'm doing this. We can write k over m as the square root of k over m squared. And I'll show you why. The inverse Laplace of s over s squared plus a constant a squared is nothing other than the cosine of the constant a times t. Right? So we get that x of s is equal to d times s over, s squared plus the square root of k over m squared. If we take the inverse Laplace on both sides, we get that x of t is nothing other than d times the cosine of square root of k over m, all multiplied by t. This is our explicit expression of x at any given point. And note that when t is 1, this just simplifies to d, which makes sense. I mean, sorry, when t is 0, this all simplifies to just 1, yeah. So, which makes sense because at the initial point in time, this is x units away from the rest point. And here x measures distance, no, x measures displacement, because this can take on negative values. So this point here is negative x. And this is an explicit function for the position of the spring. And if we remember that the net force is equal to the mass times the acceleration, we can actually derive an expression for the force on the spring at any point. Because remember, here we derive that mx is equal to negative kx is equal to mx dot double dot equal to negative kx. Well, we've got x here. We know what x is. Therefore, the force on the spring, the net resultant force on this spring, is nothing other than negative k times d times the cosine of the square root of k over m times the time. And this is actually a function of t. This is solved. So if we know the spring constant, the mass of the spring, and the initial distance away from the rest mass, we can calculate the spring's position at any given time using this equation, and we can calculate its force using this equation. We can also calculate its acceleration by differentiating this twice, which is very simple. We just get that x double dot of t is just d, negative d times the cosine of the root of k over m t multiplied by k over m squared, which is just negative dk Donkey Kong over m times the cosine of the root k over m times t. This is the acceleration. Oops. Of the spring at any given time. And here we are. Here is everything you need to know about an oscillating spring. In fact, you could measure these values and rearrange in order to calculate the spring constant if you so desired. If you know the mass of the spring, you know its acceleration at any given point in time, and you know its position at any given point in time, you can, in fact, calculate the spring constant. But that's irrelevant for right now. I hope this video was fun. I know I enjoyed it. It's quite nice when you use Lagrangian mechanics, how the right answer seemingly spits itself out. And you could use Newtonian mechanics to derive this. You'd get the same answer. And similarly, you could use a technique that wasn't the Laplace transform to solve this differential equation here. But overall, I think using these two methods is quite satisfying, especially at this point when you need to rewrite k over m as root k over m squared. But I hope you enjoyed it. I definitely enjoyed making this, and I hope you can take something away from it.